Hello everyone, thank you so much for giving me the chance of presenting this talk still from the distance. Unfortunately, I had a visa issue and I couldn't be in Quebec this week. I'm very sad to be missing the other talks in this theory session. I was looking forward to many of them, and unfortunately I won't be able to listen to them. At least I have this remote virtual window to tell you a couple of things about my research. Some of you might remember my presentation last year in TopoNets. I'm happy to report that there's a lot of implementation now of these new techniques and all the hypergraph rewriting technology that we've been building. And together with Lyubov Tupikina, my colleague here, we are getting ready to apply in different areas of higher order systems and complex networks. So again, thank you so much. Please do get in touch, follow these links to get access to any of our papers, and do drop me an email to at least have some replacement of what have been the in-person interaction over there. So without further ado, let me get started. So of course, we all know that we're living in a hypergraph boom. This is data that that ends in 2021, but if we had included the last couple of years, I'm sure this would even fit more closely an exponential explosion, and so I think that the hypergraphs need no introduction in this forum. Of course, we could take, for example, the higher order systems book as a reference for this sort of crystallization of hypergraph methods and techniques in complex systems. So something that has been a hot topic in dealing with hypergraphs, especially in large data sets and data sets involving high arity, is how to deal with the computational complexity and the risk for combinatorial explosion. Now, one of the often used techniques is to do order reduction, essentially take hyperedges and reduce them to their binary components. So here, my colleague Lyubov has generated two visualizations of a weighted metric called the cognitive distance that effectively does some sort of weighted distance between nodes in a hypergraph. So this is particularly computed for preprint papers and the archive where the nodes in its hyperedge are categories for the listings. And so on the left you have the distance computed for the full hypergraph, so full arity hyperedges, and the right for the reduced hypergraph, only with binary edges. So you can already see an apparent difference in resolution. So it seems that we indeed miss the ability to distinguish some features when we project down to just the binary edges. So how do we understand this in a bit more mathematical terms? We like to think of adjacency matrices and what information those encode. So of course, in a more conventional graph, just a pairwise graph, we have an array that represents the adjacency data just in the form of a matrix. Now, when we move to hypergraphs, we now need to include information in two different ways. One is by considering higher arity, so we need to have arrays that are higher order, so they have numbers in more dimensions, but also we have to combine several orders of such arrays. So I would say that hypergraphs are hyper in two different ways. One, because they involve higher order edges, but other because they involve different orders of edges together. And so a hypermatrix in this case will be a representation of some kind of formal sum, where unary edges are represented as a vector here, binary edges are represented as a matrix here, and ternary edges are represented as a cubic matrix or cubics over here. So what is the benefit of considering adjacency hypermatrices? Well, the benefit, and in this case I just want you to look at the right half of this diagram. The benefit is that we get access to generalized linear algebra and generalized algebra of adjacency tensors. I will make a comment here. Some people might want to call these tensors because indeed it's a popular term to use. I really like to stay away from that term because there's no multilinear structure of these objects. So I prefer to just call them hypermatrices or arrays and be a little bit more cautious in that way. But so indeed the main advantage of this is that we get access to generalized algebras of these objects, of these arrays of adjacency data. And of course you can look at the first line here. You would recognize the ordinary matrix multiplication, which we all know is a binary associative algebra that the properties of which allow us to usher a whole wealth of techniques in analysis of graphs, in spectral theory, all the kind of algebraic graph theory tools. And in the case of higher order arrays, so things like this Bijk, which now has 3 indices, could be something like this, we can define other kinds of algebras. So the benefit is that we have a lot of flexibility what to do. We can consider many more patterns that might be more adapted to our problems. The price we pay is that this is uncharted mathematical territory. So there is active ongoing research dedicated to understanding this ternary, non-associative, non-closed algebras. And there's still no good theory that out of the box will give you techniques anywhere near the efficiency and the power of what techniques we have for graphs and based in linear algebra and spectral theory and so on. So what is then the point of having all this hierarchy information and higher order data structures if there's such difficulty? Well, I bring my proposal and what this project is sort of aiming at, and that's the rewriting approach. So we are trying to approach this with rewriting, and the way it works is really quite simple. So rewriting naively is simply taking a rule that will scan your hypergraph for a pattern that is on the left-hand side box, and once it finds a pattern, it will rewrite whatever is on the right-hand side box. So you can see here, if I take this initial graph, the rewrite rule would check for example, the case 3, 4, 5, and will simply rewrite a path between 3 and 5, like that. So here highlighted in blue, and similarly for the path 1, 3, 4, in which it would rewrite just the path between them. And now these hypergraphs again have those edges as part of their structure, so you can rewrite again. So in this case, you can rewrite in 2 different ways, but finally in only one way that leads you to a final hypergraph that cannot be rewritten again. As you can see, those arrows are just pointing in opposite directions, and there's no more application of this rewrite rule. So the process terminates. So it is a simple exercise to show, and I'm sure many of you are aware of this, that performing rewrites of this kind is indeed equivalent to doing matrix multiplication of the adjacency matrix. In fact, more precisely, if you take this graph, compute its adjacency matrix, then compute its square, you would be able to show exactly that that graph, the graph corresponding to the square of the adjacency matrix of the original graph, corresponds to the graph of all the outputs of this rewrite rule applications. So in this case, it will just be a graph that contains the edge 1, 4 and the edge 3, 5. And you would be able to check that that's really the case. Now, of course, this is all well and good for the graph case, but the hypergraph case allows us to probe algebraic structures that are quite murky and difficult to work with because they are non-associative. They don't have any connections to known structures. But rewriting allows us to just, in the same way, deal with the structures just from a purely computational point of view. And so, in particular, if we had a hypergraph like this one over here, we could simply say, well, what is the Zapata-Carratala product of the adjacency matrix? And indeed, we could compute it, and at first we'll be a bit mystified to look at it. It's like, okay, how do we deal with this exactly? But if we have the rewriting approach, all we have to consider is just the pattern matching and just apply the same principle as we had here. So here, the principle of rewriting just was sort of trying to recover the algebraic structure. Here, the algebraic structure doesn't really give us much, so we will take the rewriting as the main source of computational power. And so simply by applying rewrites to this ternary hypergraph, we will hopefully compute the properties of this hypergraph with respect to this kind of power matching. So this is essentially the summary of what we're trying to do. Everything is implemented in Mathematica. We have several extensions of ordinary graph theory, as in, for example, spectral theory, so higher spectral theory for this ternary and higher arity products. We have generalizations of the notion of distance, generalization of the notion of paths in hypergraphs that also require an understanding of this higher order compositionality structures, and these things are all becoming much more tractable under the perspective of rewriting, and so we're excited that we can hopefully bring some new techniques to the table. Anyway, that's everything from me. Thank you so much for taking the time to do this sort of remote presentation. Again, do get in touch with myself, and we can set up a call with my colleague and I. We can continue conversations. I'm sorry to miss many of your talks. I was really looking forward to them. And yeah, thank you so much.